when a field is a conservative field, there is a very important consequence in terms of the line integrals of this field. And that's what this following section does. Line integral of a conservative field. So let me start with the important result. And the result is that if a field F is conservative, which means that F is equal to the minus gradient of a potential field, then this is equivalent to the fact that the line integral between point A and point B of F vector field dot dr, so this is a line integral with a dot product, is equal to the potential field evaluated at A minus the potential field evaluated at B. And this is always true regardless of the path joining A and B. So let me explain this. You are used to this, especially with gravitational fields, right? So let's remember that the gravitational field is the minus gradient of the gravitational potential. So this is gravitational field, and this is the gravitational potential. But you also remember that the gravitational force is equal to the mass. So the gravitational force acting on a mass little m, so F gravitational, you remember that this is equal to m times g, right? This is the gravitational force acting on a mass. On mass little m. And therefore, this means that the gravitational force is equal to the minus gradient of another scalar field, which would be m times phi. Okay, and this new scalar field, we could call it the gravitational potential energy field of the mass. Gravitational potential energy. Okay, so if the gravitational potential of a mass was minus gm divided by r, the gravitational potential energy is equal to m times phi, which is minus gm little m divided by r. Right? We just have to multiply. So basically we took this equation and we multiplied both sides by the mass m. So we get mg equals minus the gradient of m phi. So the gravitational field, when you multiply it by m, turns into the gravitational force, and the gravitational potential, when you multiply it by m, turns into the gravitational potential energy. Okay? So basically what this means is that the gravitational force is also a conservative field because it derives from the gradient of some potential energy. Okay? And what does this mean? This means that the work done by the gravitational force between 2 points A and B, and that is, remember, the work done is given by the line integral, yeah? So work done by the gravitational force will be equal to the line integral of the gravitational force dot dr. We saw that in the chapter of multiple integration, line integrals. So the work done by this force will only be equal to the potential at A, to the gravitational potential energy. So m times the times gravitational potential at A minus m. So let me put a bracket here. So it will be the mass m multiplied by the difference in gravitational potential, which is equal to the difference in gravitational potential energy. So this would be the potential energy at A minus the potential energy at B. Right? You remember all of this from classical physics or even from high school. So the work done in moving a mass between 2 points. So you have a table or you have a mass on the floor, and there is a table here. The work done in bringing this mass into the top of the table is equal to mgh, which is the difference in gravitational potential energy. And this is independent of the path you take between A and B. So whatever path you choose, it doesn't matter how crazy your path, the work that you need is always the same, and it's equal to the subtraction of the potential energies. And that's because gravity is a conservative field. This is true in this simple case of the floor and a table, in which we can approximate G, the gravitational field, as being constant. So you can approximate it as a constant everywhere. So the gravitational force is constant everywhere. But this is also valid in the more general scales of, for example, the solar system. So in the solar system, when you have the sun and all the planets and so on, so your gravitational field, of course, depends on position. It's much stronger when you are near the sun, pointing towards the sun, and then it gets a bit weaker when you go far away. Then if you approach the Earth, you start getting a attraction towards the Earth, and so on. So you have this complex field, which would be the gravitational field, G, which depends on position. And even in this complex situation, this gravitational field is a potential, is a conservative field, meaning that it derives from a potential. And therefore, the work done in bringing a spaceship from one point A to one point B will be equal to the difference in energy between A and B, regardless of the path that you choose to fulfill this movement. Okay? So this is the importance of conservative fields in terms of the work done by these fields, or in terms of the line integral. Okay? So this very, very important physical consequence is the consequence of a very simple mathematical statement. And the mathematical statement is simply this. If a field is conservative, meaning that it's the minus gradient of a potential, then the line integral of the field depends only on the potential at A minus the potential at B, regardless of the path. And this is a double arrow, meaning that if this line integral is always equal to the difference in potentials regardless of the path, then you can conclude that the field is conservative. Okay? Let me prove this mathematically to you. And this proof is actually quite elegant. It looks mysterious on first sight, but if you think about it, it's actually very simple. So we want to prove that the integral of f dot dr moving from a point A to a point B is equal to the difference in the potentials. So the way we do is, what we do is we substitute the fact that the field is conservative. Okay, we are going to prove the arrow in this direction. We are going to assume that the field is conservative. So now I substitute, instead of f, I write minus gradient of phi dot dr. And now what can I do? Now I can write this as a vector. So this will be the minus derivative of phi with respect to x, minus derivative of phi with respect to y, minus derivative of phi with respect to z. And now this is dot product with dr. And if you remember, dr is equal to dx, dy, dz as a vector. Yeah. So now you carry out the dot product, and you get the integral from a to b of this dot product. So if you do this dot product, it's very easy to do. You get a minus over all minus, and you get partial of phi with respect to x times dx plus partial of phi with respect to y times dy plus the partial of phi with respect to z times dz. And now this is the amazing part of this proof. Does this remind you of anything, this expression? This expression is something that we call the total differential of a function. You remember that? So if we interpret our potential phi as a function, so it's a function which has inputs x, y, and z, and the output is the potential. And then I said, if I change x, y, and z by an amount dx, dy, dz, how much does phi change? It changes by an amount d phi. And d phi is the total differential of this function, and it's given exactly by this expression here. The partial of phi with respect to x times dx plus the partial of phi with respect to y times dy plus the partial of phi with respect to z times dz. Which means that our integral is simply the minus integral from a to b of d phi, the differential of the potential. And when you integrate a differential, the result is just the potential itself. So it's the minus potential evaluated at b and at a, which means minus potential at b minus potential at a. And now applying this minus sign that comes from the original minus sign here, we get that this is equal to the potential at a minus the potential at b, which is exactly what we wanted to prove initially. Let me write it there. Okay, so this is the proof for this mathematical statement. And the consequence is that the work done by conservative forces, which are forces associated to a conservative field, will only depend on the potential energy at the initial point and at the final point. Actually, they will only depend on the difference between the two energies. Okay? This is, by the way, the reason why engineers that work on space travel, like sending probes to other planets and so on, they always talk about potential wells. So let me go back to the mathematical applet showing you the gravitational potential energy of a mass. So if you have a mass in the surface of a planet, you are down here, and you want to bring that mass somewhere outside, right? Because you want to go to another planet. So you will need to expend an energy equivalent to the difference in energy between here and here. So that difference in height will be the energy, the work that you will need to do on the mass against the gravitational field. So that's why they call the gravitational potential of the planets, they call them the gravitational well, because getting outside of the surface of the planet is like climbing outside of this well. So that's the energy that you need to supply. Okay? So I hope that was clear. Thank you very much for watching, and see you in the next video.